there you go.
Okay, thank you, Susan. Hello, this is Manu Shantaram. I work at SDSC. I'm a researcher at SDSC. I do a lot of performance analysis, benchmarking work. I also part of other projects such as Open Science Chain and in general user services as well. Okay, so in today's talk, first I'll go over a case study. It's a project that I was involved in, and just to show at a high level the kind of data management that one has to do and various components that you should be aware of. Okay, one thing I forgot. Let me turn off my video so that I don't. Okay, cool.
I like your
yeah.
video.
Can you hear me?
I can hear you. I just said I liked your video. There's nothing wrong with it. Okay.
Okay, so let me just then go back to my video. In case you guys notice any bandwidth issues, let me know. I'll just cut off my video. Okay. So, okay, where was I? Yeah, first I'll go over a case study that I was involved in, just to show different components of the storage hierarchy and the complexity of a actual real project that one could encounter in a HPC system. Then I'll talk about why and what is data management and tools and frameworks that support data management. Then we'll spend some time on file systems, specifically targeting expanse. As I'll show in a few slides, there are multiple file systems on expanse and what are the pros and cons of using them. And I'll spend some time on Lustre file system, which is the major parallel file system on expanse. And finally, I'll cover basic evaluation. Here, what I mean by basic is it's not an evaluation or anything. I just want to show a demos with an example run on a couple of file systems to show how it varies in terms of performance. Okay, so that is the overview. And the case study that I mentioned is, so this was a project involving Oregon State and their Genomic Institute, where they collect a lot of data related to planktons using undersea camera, and they ship all the data to their center, do some pre-processing, then they send it over to HPC system. Then it was Comet, so they would send it to that. They would do some kind of analysis on Comet CPUs, then they would move the data to Comet GPUs, do some analysis, and then move the data back to their center. So this was a pretty complex process. Okay, let me just a minute. Okay, so this is the workflow that they had. Basically, they go on deep sea expeditions and have some undersea cameras. They collect data, push it to their center, which is CGRB, stands for Center for Genome Research and Biocomputing. And they have a permanent storage there. They do a bit of processing there, and then they transfer the data to the CPU nodes where they do some sort of segmentation. Then on GPUs, they do actual classification, and finally transfer the data back to CGRB. So to summarize the workflow, first, they need to copy their code on the supercomputer. So they copied it to home. And once you while doing copy, after that, you need to log in. For that, you use SSH. And they had a bunch of scripts. One of them was called as file processing script. It used different utilities like rsync to sync between synchronize between the data on the supercomputer and data at CRGB, CRGB. And the other file that means there were more than this, I'm just having these two files here. The second one, it copied whatever the tar file from project space, which corresponded to a Lustre file system, to a local SSD, which corresponds to a local hard drive that you can access once your job is running. And they did a bunch of runs on local SSDs and then shipped the data back to the project space and from there to their center. Why do you need to do all these things? There could be multiple reasons. In this case, a lot of deep learning kind of applications involve so many images, and if you store them on Lustre, it could be problematic, not just for the user, but also to the system. And running such applications on local SSDs, it runs faster. So this is the basic workflow. Now, given that we know a practical project, how it works, let's get on to the data management part. So these cartoons just show the perils of not knowing what data management is and not doing any data management. So what is data management now? You can just say data management is like managing data before and after computation. For example, from the case study, collecting data is also part of data management, like going into undersea expedition, clicking images, storing all those images in a hard drive, copying from the camera to the hard drive. Everything is part of data collection, and moving the data from the hard drive to a server and server to the supercomputer, copying. And after all the processing, you sync the data back. So it's like managing data before and after the computation. Or it could also be managing data during the computation, because, okay, you have all your data and you run it on your local SSD, you compute everything, it outputs something. The thing about local SSD on at least Expanse and was on Comet is once you're done with your job, whatever data is on local SSD gets purged. So you need to move the data back to Lustre file system. So that is during the computation. And also note that when I talk about storage, it's not just disks. Even the memory is part of your storage hierarchy. So how you stage your data from SSD to memory is also important. Say you want to run your job on GPU, you know that it can hold, say, 32 gigs of data. How do you manage that? And finally, I just put this in. Data management is usually managing data between different storage systems. There is also provenance and integrity, which is really important if you're managing data and want to track the evolution of your data or data sets. So in this presentation, I present one slide on a framework that we have at SDSC that supports users or researchers who want to track data provenance while managing their data as well. So now we saw what is data management. Now, why do you need to manage data? First thing is there are a bunch of data sources, and it could be from sensors, like there is a Wi-Fi project in SDSC where sensors collect data and somehow pass it to clusters that compute on the data or perform analysis. And I just showed an example of undersea expedition cameras. There could be images from satellites that one want to analyze. And the traditional HPC where you run a large job where it generates a bunch of data from, say, simulation of stars or whatever, galaxies. So these data that gets generated have to be managed. And the other reason for managing data is any HPC system would have different storage mechanisms or different storage technologies. You need to know which ones to use for different purposes. Means if you have a very small file, where do you need to store it? If you have a very large data set, where can you store it, or which is the ideal place to store it, and so forth. And that is in terms of capacity. You should also think about performance and scaling of your application. Once if I store it in a particular place, can I scale my application, or do I need to store it somewhere else? So these are the things you need to know. Hence, you need to understand data management. Okay, I covered this part. So now moving on to the tools for data management. So Globus is a widely used tool for data copy. This is the Globus URL that one can use. I'll just show a demo after the slide to show how you can transfer data to and from Expanse. And this particular Global Connect Personal, this is used on your local system. For example, I'll show it from how do I transfer data from my laptop to Expanse, or Expanse to my laptop using Globus Connect Personal. And finally, there is a very useful link that shows data management techniques. Basically, it expands on whatever I have shared right now here. So let me just come out of the presentation and go to the Globus URL. Let me know whether you all can see it. Can you see this URL?
Yes.
Okay,
Yep.
cool. So first thing is, okay. What was the? Okay, so here there is a login. If you are an Exceed user, then you can log in using Exceed, or I think depending on the university you are in, you should be able to log in using Globus. I'll just put in my Exceed credentials. And I hope it will work. Okay, so now it requires a dual form of authentication. So I'll just give it my Duo. So once I log into Globus, this is what I see. Once it says, it gives you two places, like you can consider them as source and destination. So let's type Expanse. And if I do this, okay, it retrieved my Expanse. But notice that sometimes, if you're doing it for the first time, probably it will ask you to again log in. That happened to me once. So this is my Expanse home directory. And now say I want to transfer something from Expanse to say Stampede, which is another supercomputer at TAC. So this is my Stampede directories. So let's see, I want to transfer something, right? Let me just, I don't know. I hope it's not too big. These are pretty big files. I don't want to do that. Okay, so let me go to, this is my Expanse. I go to bin and say, I copy this to my bin on Expanse, right? Now, I'm on Expanse and there is bin. And if you look at this IB run has been copied from my tag to my Expanse home directory. So this shows how you can transfer between two different systems. I can also transfer from my laptop, for which you need to use Global Connect Personal. I have already installed it and my laptop is already stored, I think. Yeah. And here you should be able to see the contents of my home on my laptop. So this way you can use global web interface to transfer files. And this is the link that I was talking about that talks about data management in general and on Exceed resources or in general. So this is a very useful resource. You can go over it. And there are a lot more options in Globus, which I'm not going to cover, but you guys can explore it. Now going back to the presentation. Let me see. Okay, Mary is answering. Okay, cool. So go back to my presentation. Okay. So this is a command line interface tool. Not command line, sorry, web interface. Command line option is also there, but what I illustrated is web interface. And usually you use Globus if you're transferring a lot of data and large amounts of data. Now, SCP and SFTP are good command line utilities to transfer some files, small files, say less than 2 gigs. And I just took a snapshot of MAN, SCP, and MAN, SFTP as to what they do. SCP is secure copy. SFTP is it's a file transfer protocol in a secure way. And both can be used for file transfers. And there is also rsync that I had highlighted in the case study. So here it is similar to SCP, but a lot more versatile than SCP. You can actually sync between two directories on two different hosts or within the same host. You can give it options so that it doesn't override the existing files. It's pretty powerful, and MAN page on rsync would give you various details.
Manu,
Yes.
we have a couple of questions. A first one early on was really how do you use rsync, and are there any security requirements? And then a couple people want to know why exactly is Globus better than SFTP? And if you could take a moment and answer those questions. What are the requirements to use rsync between Expanse and a remote system?
So you would have to have some kind of credentials to say if you want to do a SCP or rsync from my laptop to Expanse, then you should have whatever credentials that you need to log into Expanse. And I think that is about it. If you're able to do SCP, you should also be able to do rsync.
So the SSH credentials
Yeah,
that you
basically,
typically,
yeah, you should have SSH credentials to do any of these. These are, I think, have underlying implementation as SSH as well. So
okay,
yeah.
Sorry, and so then another question is, what's the advantage of Globus over SCP?
Yeah, so one advantage that I can think off the top of my head is Globus allows you to do large file transfers. Means even in SCP you can try, probably it will fail. Say you want to transfer hundreds of gigs of data, then probably it would fail, or it can time out. I don't know. I have not tried it, but traditionally users use Globus to do large file transfers, and the endpoint on Expanse for Globus is a data mover node, which is pretty good for moving data, which is what we also recommend because of its high bandwidth.
I think that kind of answers a couple of the other questions. So we can have more discussion later on when you're
done. Yeah, I think we'll
perhaps.
have some time during the.
Okay. Yeah.
Okay, this is. Okay, so these are the traditional data management tools that we use. Now coming to Open Science Chain that I mentioned earlier, it's a CI platform that CI as in cyber infrastructure platform that uses some blockchain technologies to store information about data sets or data in general. And it can be used for provenance tracking or metadata management. Here is the URL for that. And this is very useful if the data set that you are using is evolving and you want to know what changed in the data set. Basically, some kind of provenance tracking. So you can go to that URL and get more information on that. The other repository is HPC Share, which is a service provided within SDSC that can be used to share data for collaboration purposes. And this is the URL for that. This HPC Share has been developed on top of SeedMe Lab, which is also a project within SDSC. And these are the benefits of using HPC Share. It allows you to do some visualizations on certain file formats interactively on the web. And yeah, so these are the two other ways that you can use for data management. Okay, so now we'll move to file systems. Why file systems? Basically, you need some place to store data as files or directories or whatever. Usually these files get generated when you compute. Hence, whenever you compute, you need file system. Also, you would want to store your checkpoint. Checkpoint, by checkpoint, what I mean is, say you have a long running simulation which runs for days together. In general, HPC systems allow you to run for say 48 hours or there is a time limit. So you want to checkpoint your data so that you don't lose anything when your job ends. Then after 48 hours, your job would be probably killed. You restart your job with the checkpoint so that you don't lose anything. So even for that, you need file system. But the kind of file system you use for different things like storing thousands of files or checkpointing might be different. So here is a technical summary of Expanse system. Without the slide, my presentation would be incomplete because since it is about Expanse file system, I thought I'll just put a slide on technical summary and go over this very quickly. Basically, Expanse has a bunch of compute nodes, like it says, I don't know how many, but yeah, 728 compute nodes, which have AMD EPYC processors, and each of them have a bunch. DRAM itself is around 256 gigs, and it has NVMe local to each node, 1 terabyte. And there are GPU nodes, there are large memory nodes, and storage, various storage options. And the figure here shows how Expanse system is arranged. For the purpose of this presentation, we are mainly interested in these circles, which are like the storage part of Expanse. So as you notice, there are various storage technologies used in Expanse. One of them is node local NVMe drives. These drives are not shared across nodes. So that is one thing you need to be aware of. There is parallel file system, which is shared across all the nodes, both compute and GPU nodes. There is network file system, which is specifically used for users' home directory. And we also have Ceph Object Store, which is coming soon, but it's in the works. So there are four file systems that I listed, but apart from that, you can also have your main memory. So why do you need different file systems? First one is performance. You would want your application to run fast. Hence, you need to pick a file system that performs well. say if you want to scale your application across nodes, and you would want to write into some location which can be used by across nodes. So you need some kind of a shared access across nodes. Hence, you have the parallel file system. And backup and long term. Yeah. Among the file systems, not all of them are backed up. And typically, some file systems are only used for scratch purposes, as in temporary storage. They get purged after a certain point. So, but you use them because of certain characteristics of your application, for example, local SSD. And finally, in terms of quotum, how much, once you can't store too much data in your network files, NFS storage, although it is backed up to a certain extent, you can't store too much data because you have 100 gigs. And it is primarily used to store important files and not used as a parking space for data. For that, we have other options at SDLC that we can discuss later. Okay, so now we saw different file systems, although I didn't go into where these file systems are located and Expanse, which I will, but you should have had an overview of various file systems. This example, I ran some code on 2 file systems on Expanse. The first one, okay, oops. Okay, here it shows the capacity of the file system, this benchmark. One has capacity in terabytes and the other one in maybe a terabyte range. The figure on the left was on parallel file system, whereas the on the right one was on local SSD. So this, just a minute, I need to hide the front. Okay, so this shows the performance in terms of bandwidth that one would achieve on either of these file systems. You see that it varies a lot. It's exactly the same application with same parameters, but run on 2 different file systems. And you see widely varying performance. So you should be aware of these things when you try to run something on Expanse. Okay, so basically, storage choices should be driven by application need, not just what's available. So I have a lot of small files, a lot of data, and parallel file system it provides a lot of capacity. So is it good to store that? It depends. So yeah, you need to see what is the kind of computation your application is doing and how you want to scale the application. Based on these, you select a file system or a subset of file system to use for different parts of the computation. For example, if you are writing say few as in say tens of small files into your home directory, it's okay. But if you're trying to write thousands of such files, then probably it'll kill the NFS server, and not only that, it will affect the entire system. So you should be aware of this. Now let's go on to Expanse specific file systems, as in where in Expanse do you see these file systems. Once you log into Expanse, you see your home directory. And there's a variable set as $home, which is your home directory. So as I go through next few slides, I'll also toggle between the terminal just to show you where it is. Okay. So now let me increase the font size because I think increase it. Okay, do that. Yes. So is the font size good enough?
Yes, that looks good.
Okay, cool. So if I do echo $home, yeah. So you can see that is the home directory and that is the NF network file system storage place. As I mentioned before, it is typically used to store source codes, important files. For example, I have I benchmark weather forecasting codes. So I just download the source from the Git and store the source, compile the source, and maybe even store the binary if it's not too big on this file system. Whereas the data that I download, which runs into tens of gigabytes, we have to store it in a different place. The storage limit for this is 100 gig. It is backed up, but as I mentioned before, please don't use this space as a parking space for your data. This is not the right place. We can talk about various places that you can store and are backed up, because parallel file systems that we have are not backed up. So the next one is Lustre Scratch, which is under this location. So let me go to this. Lustre Scratch. Okay, here $user won't work for me because, let me see whether it will work. Okay, it did, good. User, and so this is the place where you store all your temporary files or whatever data you want to analyze. But know that this is not a permanent storage. So it will get purged after 90 days. And it's in general a good practice to clean up your data after you're done with the data, rather than just store it and forget, so that the entire storage, Scratch storage, has enough space for all users. And this is not backed up. And not only it is not backed up, it gets purged after 90 days. And this 90 days is creation time. So even if you go and modify it, say on the 89 day or 88 day, on day 90, it will be gone. So yeah, it's creation time and not the modification time. So now there is also Lustre project space, which is again parallel file system, as you can see, since it's Lustre, and it is under this. So I'm part of one project, so I can probably go to that. Okay, and so basically this is the project space which gets assigned per project, and it stays there for the duration of the project. So make sure if your project is ending, you somehow back up the data. This is the detail of this particular space. And again, this space is not backed up, but the space will be there till your project exists. Once your project is done, this space will not be there or may not be there. Okay, next one is the local SSD storage. Okay. It is present in this location, which is Scratch, user, job, and Slurm ID. Here, note that this particular storage space is not accessible when you log into Expanse. Only once you start something on a compute node, you can access this storage either through the job or directly logging into the node once you have your job running on the node. So let me just show you where that is. It is Scratch. What is it? Scratch user. Once you go there, there is one directory. So this is my local SSD. So, okay, let me just increase the font size of this as well. Okay, and let me exit this. Okay, so here I'm on the login node of Expanse. here I shouldn't be able to access that particular scratch. There is no directory because that is specific to a compute node. Okay, these are the characteristics of this NVMe SSDs. It's typically used to store large number of files, and you need fast access, high IOPS, and the storage limits, it depends on where you are computing. For example, on compute and shared partitions, you can get 1 terabyte of storage space in this. And on large shared memory nodes, you can get up to 3.2 terabytes. And as I mentioned before, this is only accessible during your computation. That is, you need to have a node for your job. Only then you can access this. And this is purged after the job. So make sure you copy the data back onto any other storage before your job ends. Otherwise, you'll lose all the data. Okay, here is the very quick version of whatever I covered till now. Basically, it says, it illustrates various attributes of different storage. This is a nice guide that used to pop up whenever we logged on to comment. Right now, it is not there for Expanse, but I thought I'll just put it up so that you can see the kind of thing that you should use Lustre file system or your NFS file system for. And this gives a rough estimate of the kind of capacities and performance in terms of bandwidth we could expect from different storage technologies. Note that the numbers like 100 Mbps and 500 Mbps may not be really accurate. I just wanted to show how it would look in terms of the difference in magnitude of performance or capacities. Local file systems are good for small temporary files, whereas you need a parallel file system if your application has high into bandwidth. Okay, let me check if I have any questions. Okay, Mary is
There are
answering.
quite a few. I've been answering some, but what is the storage limit in Lustre Scratch?
So that is kind of not really well defined. Means you can get around 1 terabyte, I think. And based on the project needs, maybe you can ask the user services to increase it or decrease it. I am not 100% certain if there is a preset limit, but I would assume it is around 1 terabyte.
Another question that might take you to answer is on Expanse compute nodes, where does one write files to use the local NVMe?
Oh, so that is the Scratch that I talked about. So I can go here, right? Yeah. So that is the Scratch, $user and job and your job ID. So this is the actual NVMe drive. And
Okay.
you can access this only on a compute node. Okay. So are there any other questions, Mary, or can I?
You can go on, thanks.
Okay, cool. So now, okay, I won't spend too much time on Lustre file systems as we are probably will run out of time if I go in depth. So this is a basic overview of Lustre file system. You have different components. One of them is MDS, which is the metadata server. The other one is the OSS, which is the object storage server, and Lustre clients that we see as users. Metadata server is generally used for metadata kind of operations, like when you open a file, close a file, or see the listing or files under a directory. There's a call to the metadata server. But if you're performing IO operations like reading or writing continuously, then the Lustre client talks to OSS directly instead of MDS. I'll probably cover that a bit. So typically a Lustre file system would look like this. You have a bunch of clients. You can think of your process on a compute node as a client if you want, because all your compute nodes are clients, and there are a bunch of MDSs and bunch of OSS, object storage servers. And here MDT stands for the target where your data actually gets stored. So server is a server, and MDT is more like a disk or a NVMe. It could be anything where your data gets stored. So that is MDT. OST is similar to that, but it stores actual data and not the metadata. So this is the summary of Expanse files, Lustre file system. Basically, it can support up to 12 petabytes of raw, but since we don't use raw, it's around 11 petabytes overall. This includes both the project and the scratch space. And I think these are the derived metrics from 11 petabytes, saying it can store around 1 billion files. That corresponds to the number of inodes that it can support, I think. And in terms of aggregate bandwidth, if you utilize everything really well across the entire system, you can reach up to 140 gigabytes per second of bandwidth and 200K IOPS. We also have a feature called as data on metadata, which is DOM, for small file performance. So this is a feature of newer Lustre versions where you can store some amount of data on metadata server so that you don't have to like go to object storage OSTs, so that you can improve your performance. I have not tested them on Expanse, but yeah. And on Expanse, there are 4 MDSs and 8 OSs. And there are commands which you can run as a user to see what these are. I'll probably show those commands if we have time. Okay, as I mentioned before, there is a client, which is your compute node or even the login node. And there is MDS and OSS. Whenever you try to do any kind of file operation, like file open, close, directory search, find, all these operations involve metadata of the files. So it has to contact the metadata server. Once, say, you open the file and start writing into it, it'll contact first it'll get some information related to the OSS, and it'll start writing to the OSS directly. So that is the way it works. So given that you somehow know what is the kind of operation, what is the flow of operations, you should be aware of what kind of operations you shouldn't do. For example, you shouldn't just keep opening, closing files like every second. Then it will cause issues with the MDS, which will eventually cause Lustre issues. Okay, now going to how the actual file looks according to a user and how it is stored internally. So this is say you have a file with n+2 segments, as in blocks. For a user, it is stored in a contiguous fashion. Say when you create this file, you want the stripe count to be n, and size of each stripe is SZ. Then within OSTs, it gets stored in this way. Like chunks of your file get stored in a particular OST, and that chunk is determined by your stripe size, and the number of such chunks is determined by the stripe count. And why is striping useful? Maybe some of you would have guessed it. Say you have a very large file that you want to store that doesn't fit into one NVMe or one disk. then you can use actually Lustre to stripe it across multiple OST and store a large system. The other main reason I would say is to increase the bandwidth of access of your file system. So I saw that there is a hand raised. Okay.
That hand has been raised from the beginning, so.
Oh, is it okay?
Yeah.
There are no questions then, right? Okay, cool. Okay, this is done. So another reason is you can improve the bandwidth because you'll be accessing different OSs simultaneously. Okay, now coming to the Lustre commands. So there are a bunch of commands like LSF help will list all the options that one can have. Okay. I haven't tried this. Okay, minus help. This. Yeah. So basically you have bunch of these commands and LSF, OSTs, MDTs, get stripe, and I'll just illustrate what each one of them does. So LFS get stripe, some data, some file will tell you what is the stripe count for that file. Means how many OSTs are how many OS across how many OSTs this file is striped. So in this case, you see that stripe count is 1. And the first one gives you actually more information than what is required. The second one and the third one gives you the exact information you want, for example, stripe count and stripe size. So there is also set stripe wherein you can specify the stripe, the number of OSTs across which you want to stripe the file. So here I set the stripe count for this particular test out as 16. And when you get the stripe, you see that it is 16. And you also see the identifier of the OSTs across which it has been striped. So, okay, I'll probably cover this, but anyway, I'll mention it. So, depending on the size of your file, you might want to stripe it or not stripe it at all. For example, if the file size is too small, say in MBs or say even a gig, then you might not want to stripe it across different OSTs. Whereas if your file size is high, say runs into tens of gigabytes, then you would want to stripe it across multiple OSTs, not only because it is large, but because you can access the file simultaneously from different OSTs. Okay, again, this is an example of how do you set a stripe. Initially, I had given a count, but this is a special count -1. If you do that, it will stripe across all OSTs. Ideally, you wouldn't want to do this. I'm just illustrating it here. Okay, and in terms of directory, whenever you create a directory with stripe, a size, and a stripe size, whatever file you create within that directory will inherit that property. So here I created a directory and created a file, and that file has that 4 because the directory was created with that. However, note that if there is already a file before you set the stripe, then that file striping won't change. Okay, this is general guidelines for using Lustre file system. Basically, please do not use ls-l or with color, wildcard searches like star.out or recursive searches like grep -r kind of things. And why do you think you shouldn't do that? Because all these operations are metadata intensive, so it'll hit the metadata server. And you can say that metadata servers are kind of Achilles heel for Lustre. If that goes down, then nothing works. So you should be careful of what kind of operations you use. And you should set your stripe count and size appropriately. And you need to experiment with your application to see what is the best. And do not store too many files in one directory, because if by chance you do ls on that directory, then it's a heavy metadata operation. Okay, let me see. Okay, we have like 5 minutes. I don't want to get into demo, but I'll see if there are any questions, and I'll probably try to answer those. What do you think, Mary?
Muted. Yeah, that sounds fine. I have a quick question. What
Yeah, sure.
module, or is there a module users need to load in order to access the LSF commands?
No, it's by default there. You don't need
Okay.
to load any module.
Okay, great.
At least I didn't load any module, but since you're asking it, let me try it out. Okay. Yeah, you don't need any modules, Mary.
Okay, great. Any questions, folks? Now is your time.
Let's talk
There's
here.
you can look at the chat if you want, Manu.
Yeah.
And make sure my answers are good. Maybe some details on how purging works. And along those lines, some comments about doing, high file IO for AI applications. Small file management.
Yeah,
Okay.
means as I illustrated in the case study, if you have like a small file IO, or if you have millions of images that you process, it would be a good idea to do most of the processing on local SSD. As in, you copy your tar gz file, which has million images, onto your local SSD, untar it, perform whatever analysis. And if the output is not, again, millions of small files, you can write it back to the project or the scratch, or if it is, again, millions of such small files, write everything onto the local SSDs, tar it up, and then push it to one of these storage spaces, a parallel file system spaces, before you end your job. So that is if you're using millions of files. Whereas if you're running a weather forecasting simulation that does a lot of checkpointing, as in big checkpointing file, then probably you're better off using the parallel file system. And how does purging work? So in terms of purging, if you're on local SSDs, then as soon as your job is over, it gets purged. So please do not plan to store anything on your local SSDs. In terms of local scratch, not local scratch, which is the Lustre scratch, purging happens every 90 days automatically. So if you created something today, and on the 90th day, everything in that directory will be gone. So basically, that is the policy. Whereas if you want to store for a longer term, then you can store it in projects where there is no purging. But note that none of these have backups.
Yeah, that's a key issue.
Yeah.
Here's another interesting question, Manu. This is a bit of an aside, but speaking of Globus security, are there any issues with people spoofing endpoints?
So I am not sure. Probably Scott would be the right person, but I think spoofing, I don't know, means to at least to log in, and I don't know, Mary.
Okay, yeah, it's a complex question.
Yeah, I don't know how one can spoof.
The Globus architecture, they're one of the early developers of distributed security. So I imagine you can raise the bar really, really, really high, or really, 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 really extremely high. And Globus is at the extremely high end. So if you're confident with the security overall of Exceed services, then Globus is at the top of that group.
Correct. because I remember when I logged into Globus and tried to connect to Expanse endpoint in my first try, it actually redirected me back to Expanse login. So maybe that was just one-off thing, but I think it's pretty secure.
Especially the ones set up by Expanse
Or
infrastructure.
exceeding, yeah,
Exceed,
Yeah.
Exceed and Expanse.
yeah.
How do we access project space, quote unquote, project space?
So you can access project space using this particular location. Expanse, Luster, and there is projects. So once you go here, ideally you should know the project ID. For example, I know that I'm part of this, so I can access this. Or
Are you
I'm
sharing
part-
screen, Manu? Or Manu,
Oh,
are you?
sorry. Okay,
Yeah,
I
that's
stopped
okay.
sharing. Okay, now is my
Yes,
okay.
thank you.
So basically, this is where you Expanse Luster projects is where all the projects are located. So these projects probably corresponds to Exceed projects, I think. These are not the projects directory from, say, RDS or others, I think, but I might be wrong. So basically, this is the place where you access your Luster related projects. And this is the project ID. And yeah, that's about it. And this is the project space for Luster. Please remember that this is not the other type of project space that is also present in SDHC.
There's a comment where somebody asked, do startup allocations include project space on the backed up Luster space? Luster is not backed up.
Yeah, it's not backed up. Luster
Yeah.
is not backed up. So there is no backed up concept of backing up. But is there a user specific project space? Yeah, there is no user specific project space. It is specific to a project. But as a PI, as a user, you can add more users on Exceed or wherever, and you can create a directory for the user within the project space. What is the general terminology for the location of storing your? It's a Luster Scratch.
All right. I think one final question here. Did you catch that one, Manu?
Is it the last one related
Yeah,
to terminology?
the general terminology.
Yeah, we call it
So-
Luster Scratch. And
Okay.
within the compute node, we call it node local scratch or node local SSD. And I don't know, means if you attend the 101 tutorial whenever Mary or somebody gives, they'll probably talk about some of the variables that are already present in Slurm, which is the scheduler, using which you can access these different spaces.
Okay, so we're 4 minutes over, so I want to go ahead and wrap it up and thank everybody for staying around and asking such great questions, and feel free to contact Manu or myself, and or Exceed staff with your questions. The Exceed help group is very, very supportive. They're available 7/24, and any question really is not too simple for them. They'll be happy to help you resolve. And especially if you're having a lot of small file IO issues, those can affect not only your work and your computational time and job turnaround time, but the entire system. And so it can impact a lot of users. So if you feel like you're having some issues there, or you want to define some requirements, that's a great question to take to the Exceed help people. They can help you figure out optimal ways to manage your files.